the rectangle, top of page 1. Okay. In section 4.9, we define the indefinite integral. Given a function f, the indefinite integral of f denoted by this notation from Leibniz, right? This notation means take the antiderivative of little f of x with respect to x. The indefinite integral is the most general antiderivative of little f. If big F is the antiderivative of little f, then the indefinite integral of little f with respect to x is big F of x plus c. Right. Little f of x is called the integrand, and the variable x is the variable of integration. Right. So this is all section 4.9 material right here. Okay. And you know the rules of antidifferentiation. Now in this section, right, it's all about finding the antiderivative of an integrand that we can't just use the basic rules of antidifferentiation. We got to do something different. We got to manipulate the integrand. So we have the indefinite integral of f of g of x. Now you should recognize f of g of x, right, is a composite function. G of x is the inner function, right? With chain rule, we reviewed composite functions, right, from pre-calculus. And f of x, right, is the outer function. Well, this composite function is being multiplied by the derivative of the inner function, g prime of x, okay? So our integrand, right, is the composite of f with g, this composite function, times the derivative of the inner function, g prime of x. Okay. How do we find that antiderivative? What we do was called a variable substitution. We're going to transform this antiderivative into a problem where we can find the antiderivative using the basic rules of antidifferentiation. So we're going to do what's called a variable substitution. We're going to substitute variable u, for the inner function g of x. Okay? So u is a function of x, right? We often write y as a function of x. Well, now it's u is a function of x. Okay? And if I differentiate both sides of that equation with respect to x, I have the derivative of u with respect to x is equal to g prime of x, right? The derivative of u with respect to x is equal to the derivative of g of x with respect to x, which we denote with g prime of x. So if I multiply both sides of this equality by dx, I have dx times the derivative of u with respect to x is equal to g prime of x dx. Now this on the left forms what is called the differential, and that differential is just equal to du, and dx over here is the differential. So what I actually did was multiply both sides of this equality by what's called the differential dx. Okay. Now, One thing about how the left hand is equal to du, the derivative u respect to x is not a fraction. It's not a quotient. But if we pretend for just a second that it is, we know when you multiply a fraction by its denominator, what you multiply in the denominator cancel. And in this case, you're just left with du. So we can pretend for just a second that we're multiplying a fraction by its denominator. And the dx is canceled, and you're left with du on the left. So now when we do our variable substitution, we replace g of x with u, right? Because we set g of x equal to u. And g prime of x dx is now equal to du. And now we've transformed this problem that we couldn't find the antiderivative of into a problem where we know how to find the antiderivative. And the antiderivative little f of u is big F of u plus c. And once we find this antiderivative in terms of the variable u, we replace u with what we set it equal to, g of x. And so the antiderivative of our original problem is f of g of x plus c. So we can't get the antiderivative of our original problem just using the basic rules of antidifferentiation. But we transform the problem into a problem we know how to find the antiderivative. And we take the solution to this problem to get the solution to the original problem. And so that's what's going on here. So if you flip over to page 2, we'll demonstrate this technique with some examples. So we want to find the antiderivative of 4 times 4x plus 3 to the 100 power. Now we know how to find the antiderivative of 4x to the 100 power. Right? Bring the 4 out front of the indefinite integral. Find the antiderivative of x to the 100 power. And by the power rule, that's equal to 4 times x to the 101st power over 101 plus c, right? By the power rule. That's 4.9 homework. Okay. Well, we can't just add 1 to the exponent and divide by 101. Okay? Because this is a function of x inside parentheses. This is actually a composite function. So, to find this antiderivative, we set u equal to 4x plus 3. Because 4x plus 3 is the inner function. Okay. It's inside this bigger function. Well, the derivative of u with respect to x is equal to 4. And then if I multiply both sides by dx, I get the differential du is equal to 4 dx. Inside the integrand, this is 4 times 4x plus 3 to 100, I can switch the order of multiplication. So that's equal to 4x plus 3 to the 100 power times 4 dx. And now if I substitute u for 4x plus 3 and du for 4 dx, I have the antiderivative, the indefinite integral of u to the 100 power du. Now when you do the variable substitution, when you're all done, there better not be an x anywhere, only u's. Okay. Well, we know how to find this antiderivative, right? We just did it over here with the variable x. So the antiderivative u to the 100 is 1 over 101 times u to the 101 power plus the arbitrary constant c. Well, we need our antiderivative in terms of the variable x. So we do a reverse substitution. We set u equal to 4x plus 3. So we put 4x plus 3 in for u. And that in the box is the antiderivative of our original problem. We don't have any basic rules of differentiation that allows us to find this antiderivative directly in terms of x. We have to do a variable substitution. Then after we do the variable substitution, we know how to find this antiderivative. And so once we find that antiderivative in terms of u, we substitute for u, and now we have the antiderivative of the original function. Okay. That's what's going on here. Okay. Any questions on that? Okay. All right, in the next example, we have the antiderivative of 3x squared times e to the x cubed power. Okay. So it's 3x squared times e to the x cubed power, right? X cubed is an exponent number 8. Now, whatever you set u to, you gotta ask yourself, what's the derivative of u with respect to x? And is that derivative inside the integrand? Okay. Well, you notice that x cubed, derivative of x cubed with respect to x is 3x squared. So a good candidate for u is the exponent on the number e, x cubed. Then when we differentiate with respect to x, we have du, derivative of u with respect to x is 3x squared. And then when we multiply both sides by dx, we get du is equal to 3x squared dx. Now this middle step where I switch the order of multiplication, right? You don't have to do it. The more, when you do this a lot, you know that 3x squared dx is du. Okay. But I will switch the order of multiplication just so I don't confuse anyone. So we have 3x cubed times 3x squared dx So x cubed is equal to u, and 3x squared dx is equal to du. So that antiderivative is equal to the antiderivative of e to the u du. No x's anywhere, right? No x's anywhere. Do we know what the antiderivative of e to the u with respect to u is? It's just e to the u. And then we add the arbitrary constant c. And now we do the reverse substitution to get our answer in terms of x. Replace u with x cubed. And we have e raised to the x cubed power plus c. So that is the antiderivative of 3x squared times e to the x cubed. We don't know how to find this antiderivative directly with the basic rules of antidifferentiation, but with the variable substitution, we're able to find the antiderivative after we do the variable substitution. And then we take the solution to that problem and write it in terms of the variable x. And that in the rectangle, in the box, is the antiderivative of this original function. Okay. Any questions on that? So next we have the antiderivative of x cubed times the sine of x to the fourth. Well, the function x, the power function x to the fourth is inside the sine function, right? So x to the fourth is the inner function into the outer function, sine. And so, in the derivative of x to the fourth with respect to x is 4x cubed. And so we can still find this antiderivative even though we're missing the multiplicative constant 4, right? If your derivative is just off by a multiplicative constant, you can still find the antiderivative using the variable substitution. So we're going to set our variable u equal to the power function x to the fourth. Then the derivative of u with respect to x by the power rule, right? Remember, we're at this stage of the semester where you got to keep the rules of differentiation separate from the rules of anti-differentiation. Right? There's a power rule in differentiation. There's a power rule in anti-differentiation. There's also a power rule in the rules of logarithms. Okay? So you got to keep the power rules separate. All right, so when we multiply both sides by dx, we get du on the left is equal to 4x cubed dx. Okay. And now I can multiply both sides of this equality by 1/4. And I have 1/4 du is equal to x cubed dx. Right? Multiplying by 1/4 x to the fourth, well, let me switch to order multiplication. All right, you don't have to do this, but I don't want to confuse anybody. So when I switch to order multiplication, I have the sign of x to the fourth times x cubed dx. Now, x to the fourth is equal to u, and x cubed dx is 1/4 du. So when I put in u in for x to the fourth, I have the sign of u times x cubed dx 1/4 du. No x's anywhere. Okay. Well, the 1/4 I can pull out in front of the indefinite integral. Derivative sign is cosine, right? And the derivative of cosine is minus the sign, right? So the antiderivative of plus sine u is minus cosine u, right? Got to keep the minus signs. So we have minus 1/4 times the cosine of u. And you don't have to put the u in parentheses, but since x to the fourth was in parentheses, I'm carrying the parentheses. Okay. So this is the antiderivative, right, of this guy. After we do a variable substitution, but we need our answer in terms of x, so we do a reverse substitution. We put in x to the fourth in for u in our final answer, and we have minus 1/4 times the cosine of x to the fourth plus c. So that is the antiderivative of our original function. Any questions on that? All right, so if you flip over to page 3, we have to find an antiderivative involving the square root function. So we have 2x plus 1 times the square root of x squared plus x with respect to x. So you can see that x squared plus 1, the function x squared plus 1, is inside the square root function. And the derivative of x squared plus 1 is 2x plus 1. So a good choice here is to set u equal to what's under the radical, x squared plus x. And then when you differentiate u with respect to x, you get 2x plus 1. And then when you multiply both sides by dx, you have du is equal to 2x plus 1 dx. So 2x plus 1 dx is equal to du, and x squared plus x is equal to u. So we have the square root x squared plus x times 2x plus 1 dx now when we replace x squared plus 1 with u, we have the antiderivative of square root of u, and replace 2x plus 1 dx with du. We now have the antiderivative of square root of u with respect to u, and we know how to find this antiderivative from the basic rules of antidifferentiation. So square root of u is the same as u to the 1/2 power. So by the power rule, antidifferentiation, we add 1 to the exponent. 1/2 plus 1 is 3/2, and then we divide by 3/2, which is the same as multiplying by 2/3. So this is the antiderivative of square root of u with respect to u. And now to get the antiderivative in terms of the original function, in terms of x, we replace u, do a reverse substitution. Replace u with x squared plus x. And we have 2/3 times x squared plus x to 3/2 plus c. Any questions on that, ladies and gentlemen? Okay. All right, una mas, and you'll be experts on the substitution rule. Okay. All right, lastly, we have to find the antiderivative of the square root of the natural log of x over x with respect to x. Well, you should recognize, right, the derivative with respect to x of the natural log of x is 1 over x, right? So this inside the integral, we can split that up into the product of two quotients. Square root of log x over 1 times 1 over x, right? You multiply two fractions, you just multiply straight across. And so the integrand can be written as the square root of the natural log of x times 1 over x dx. So in this case, right, the natural log function is natural log of x is inside the square root function. And the derivative of natural log of x with respect to x is 1 over x. So a good candidate for u substitution is to set u equal to what's under the square root. So if u is equal to the natural log of x, then the derivative of u with respect to x is equal to 1 over x. And when we multiply both sides by dx, we get the differential du is equal to 1 over x dx. So now when we do the substitution, put u in for the natural log of x, we have the square root of u, and then 1 over x dx is equal to du. And again, after after we do the substitution, there better not be an X anywhere, or you did something wrong. Well, square root of u is u to the 1/2 power. And then again, by the power rule, you add 1 to 1/2, you get 3/2. And when you divide by 3/2, the same as multiplying by 2/3. So we have 2/3 times u to the 3/2 plus c, the arbitrary constant c. So that's the antiderivative of square root of u with respect to u. But now we need our answer in terms of x to the original problem. And so when we substitute do reverse substitution and put the natural log of x in for u, we have 2/3 times the natural log of x to the 3/2 power plus c. And that is how the u substitution method works. Okay. So it enables us, right? For some functions where you can't use the basic rules of antidifferentiation, okay, it enables us to find the antiderivative by making the appropriate substitution.